Hello everyone, my name is Ruchika Agarwal and today I am here to present my research paper, An Approach to Learn Structural Similarity Between Decision Trees Using Hungarian Algorithm. This paper is done along with Dr. Nanne Singh, who is the supervisor of my PhD research work. So the agenda of the PPT would be as follows, starting from the introduction, then coming to the aim of the paper, problem definition, approach, notations, proposed methodology, conclusion, and the future research that we are planning to do. Okay, so now coming to the introduction part. So as we all know that data mining techniques, they generally focus on discovering the patterns and extracting the useful information from the various facts which are already there present in the databases, right? So now what has happened is that after reading the papers, we got to know that there's a belief which says that decision tree is one of the most prevalent technique used for classification systems, predictive modeling, for interpretations as well as data manipulations. Okay, so now coming to what is the decision tree? Since we're talking about similarity between decision trees, so we should know what a decision tree is. So it's a classifier which has the ability to generate rules, and these rules are used by humans to um, strategize and to come to different conclusions depending upon the problem in hand, and at their own discretion they can come to different conclusions. And as you can see in the figure, it has two kind of nodes. um, since it is a tree-like structure, so these nodes are either a leaf node or a decision node. So as we just saw in the diagram, the two kind of nodes. So leaf node is used to indicate class labels. So we use these class labels to come to the conclusions. And the other one is the decision node, which is used for conditions. So whenever we have an attribute with us, we can apply some kind of condition using the decision node, and finally we can branch out to different paths in the tree. Now, when we say that a DT, that the decision tree is used as a classifier, so we always start at the root node, and from the root node we navigate to the leaf node, depending upon the decision nodes that are there in the middle. And finally, the leaf node which is encountered is going to be used as a class label for that particular instance. Now, in order to convert the decision tree into an AOV triple, so we have used the format of attribute operator value. So let's see how it works. So as the title of the paper suggests, that we are trying to find out the structural similarity between the decision trees, and these decision trees that we have taken could be from the same data set or different data sets. Using this approach, we'll be able to find out the similarity between the two decision trees. And before talking about the structural similarity, I would just like to clarify one thing, that similarities in general, if we're talking about similarity between decision trees, can be classified under two categories, which is structural as well as semantic similarity. So the prior study substantiates that there is no correlation between the two, and there has been a lot of research on the semantic part. If you just have a look at different research papers on the semantic similarity, you will be able to find a few papers on that. But if we talk about structural similarity, there has been research on this part, but we'll just like to improvise and have an optimal solution with respect to this. So the problem definition of a research paper is as follows, that given two decision trees, say T1 and T2, which are induced from different data sets, and we like to quantify the similarity between these two decision trees, right? So to achieve that part, we will have to firstly compare few things. What are they? They are the common regions, which is the structural similarity. Then there are semantic similarity, as I just talked about semantic similarity, which takes into consideration the probability distribution function, the PDFs. And we can also consider interpretability. So this is something that we are going to do in the future research work, and we are still doing that. And lastly, taking into consideration all three factors, the common regions, the similar PDF, and the interpretability, we are going to continue or contribute to the overall similarity of the two trees. So since we know that the decision tree has a lot of branches, so what we have done is we have that each branch in a decision tree is basically considered to be as a region, and when we are trying to compare these branches, we say we are comparing the regions, and this actually is nothing but a sub problem of the actual problem when we're talking to of comparing the decision trees together. So before comparing decision trees, we'll have to compare their branches. So that's what we've done, and in order to find out the structural similarity, we need to find out the structural overlapping, right? And earlier it was done using the brute force comparisons, wherein we are trying to compare each region with all the others. That means that for each branch in, say, a decision tree T1, we are going to compare it with every other branch in the second decision tree, which is T2. So this was not something which is, according to us, a very good solution. So we are going to improvise on that first, and later on then we are going to apply the Hungarian algorithm. So just to represent how our research is different from what has already been done. So this is in the figure, as you can see, this is the approach which is already covered. So in this case, we can see that there are two trees, T1 and T2, and for each branch in the tree T1, the comparisons are done with every other branch in the tree T2, right? And vice versa. That means for each branch in T2, the comparison is done with each branch of T1. So this is how the brute force comparison looks like. So it's, for instance, if it is like m branches in T1 and n branches in T2, so it is going to be m cross n. So to improvise on this part, our approach is different. What we have done is we have tried to avoid the comparison or the basically we have not focused on the branches which are not having any kind of similarity. So any kind of unmapped regions, we have excluded them, and all the regions which are properly mapped onto the data space, we have included them. So this is how we can improvise on our approach. So rather than comparing each and every branch with the other, we are trying to improvise on that. So having a look at what exactly we have done, so we have used these notations here. So D being the dimensional data space, and A being the set of attributes, and all the class labels that we have used are represented by using the C, and this is nothing but obviously the set of classes, and we have talked about the training set S that we have taken, and we have talked about the region R, and then we have also to compute the problem, we have used the AOVs because we wanted to represent the decision tree in some kind of format. So for that we have used the AOVs. So what are AOVs? It is nothing but this is known as attribute operator value. So what we've done is to represent the decision tree in a different format. Basically, we wanted to do some kind of computation. So we have represented it using these AOVs. And the A here is the attribute, O is the operator, and V is the value, as I just told you. And as you can see in the figure, if we are talking about this particular figure, so A is the attribute over here, X is the class label, Y is the class label, right? So if you're talking about A, we say if A is less than equal to 0.5, it is going to be X, and if it is greater than 0.5, it is going to lie under the class label Y. So here we can just write it in this AOV format or the triples, as we just call them. So we say A is the attribute, less than equal to is the operator, and 0.5 is the value. So this is for the left branch, and similarly with the right branch I can write A as the attribute, greater than sign as the operator, and 0.5 as the value. So the methodology that we have used in our research paper to find out the similarity is as follows. So to find out the overall similarity, we need to have two factors, which are structural similarity and semantic similarity. We have already talked about this. And in order to find the structural similarity, there are two things that we need to focus on. The first one being the branch level similarity, and second one being the mapping similar branches. So we are trying to do both of them here. And after doing these two things, we are going to club this up with the semantic similarity to find out the overall similarity. So coming to the structural similarity first. So in order to compute the overlapping portions, so for instance, we have got two trees and we need to compute the overlapping portions. We will have to find the structural similarity for that. So, and as I said, we need to just compute the overlapping of comparable branches. We are not going to take the branches which are unmapped. So we are going to map only the ones which are overlapping. So how will we'll get to know about that? So in order to figure out this, we have used the comparable branches which are going to have the same class labels. So any branches which are going to have different class labels, that means they are not comparable. So in order to compare those branches, we need to have same class labels, and we are going to then talk about the range, the attribute values, the range of the attribute values, and accordingly we are going to okay. So we have an idea of how do we write the AOV. Now, since AOVs have those operators with us, right? So it was very difficult to mathematically derive something out of those operators. So to simplify the whole process, what we've done is we have converted those AOVs into ALH triples. So ALH basically means that we have set the range of the attribute. For instance, if we talk about the attribute A, so we can say that the range of the attribute is say from 1 to 0 to 0.5, or maybe 0.2 to 0.7. So we are actually taking the range. So it is the attribute, the lower range, and the higher range, or the lowest value and the highest value. That's how we have written this. So as you can see in this example, if it is a less than equal to zero point 0.5 and a greater than 0.2, so we know that the minimum value of a is going to be 0.2 and the maximum value would be equal to 0.5. So for that we have written the ALH as follows. So now, depending upon the ALH that we have just got, we are going to get the value of the similarity. So that range would be from 0 to 1. That is how we have basically converted everything. So the similarity would be, if we say that the similarity is 1, that means the two regions that we're trying to compare are exactly same, they are equal, right? So it has got the exact matching. So wherein we say that the size also is going to be same, right? And when we say the size, that means the number of branches would be same, right? When we say similarity is 0, so similarity would be 0 only if the two regions that we have tried to compare are not equal. So if they are not equal, the value would be 0. If they are exactly same, the value would be 1. And if they are somewhere in between, that means they're not exactly same, neither they are like very different. So in that case, it is going to have an intermediate value. So to find out that intermediate value, we have used a formula to find out the overlapping fraction, and we can easily visualize this thing in the data space if we just create a 2D data space and we try to figure out the overlapping of the two attributes. We'll be able to find out that using this formula we are getting the value. Okay, So now after doing this much, that means we have created the AOVs, we have created the ALH, and then we have found the similarity values. We have created a matrix, and using that matrix, we have applied the Hungarian algorithm, which is proposed by Kun. And using the Hungarian algorithm, we just got a matrix, and using that matrix we have used the algorithm to find out the similarity and the solution for the same. So for instance, if we have got these two regions, so two regions basically means the branches, right? So if the first tree has got two branches and the second tree has got three branches, so we can just compare it like this and we can create a matrix, and this is how we can just figure out the values in the range 0 to 1. So in our paper, what we have done is we have used this Hungarian algorithm, and finally we were able to derive um, a formula wherein we were able to find out the similarity, the structural similarity between the decision trees, and we were able to see the exact mapping of the comparable regions. And we also saw that the unmapped regions, they basically contribute negatively to the overall similarity. So we have not taken that part. We have subtracted those unmapped regions, the value of the similarity of the unmapped regions, and doing that, we have got the exact value of the structural similarity. And further, we intend to find out the overall similarity of the decision trees, and for that, we are going to compare and combine both the things. It is going to be a concoction of the structural as well as the semantic similarity, and we are also going to consider interpretability to just find out the overall similarity between the decision trees. And it is we are planning to design an algorithm and work on the different data sets to find out the result. Thank you so much for giving me this opportunity to present my research work in the conference, and I would like to thank all the organizers of the conference for giving me this opportunity. Thank you so much.